the black of the deep ocean, a fish built like a blade is hunting something twice its own size. Its weapon is a flat-boned sword sharp enough to kill in one slash. Its target has eyes as big as basketballs and 8 arms lined with teeth. This is the giant squid, and for years scientists believed only one hunter on Earth dared to challenge it. You're about to learn they were wrong. We're about to see a shark with mystery scars, a swordfish bill snapped clean in half, and a squid dragged down by suckers strong enough to grip a steering wheel. If deep sea mysteries pull you in, hit subscribe before we go under. Take a breath. We're diving where the ocean hides its fights. A blade-shaped body rips through black water faster than a car on the highway. Nobody sees it coming. 1 second the ocean is empty, and the next a shape tears past at 50 miles an hour, maybe faster. This is the swordfish, and speed defines every part of how it hunts. Picture a school bus doing 60 miles an hour underwater. That is close to what a hunting swordfish feels like to anything nearby. Its body is smooth and scaleless, shaped like a torpedo, with almost nothing sticking out to slow it down. Even its fins fold flat against its sides when it wants to move fast. Every part of this animal answers one question. How do you catch something that can also swim away? The answer starts with muscle, and swordfish carry 2 separate kinds. One kind is pale and built for short, violent bursts of speed. The other is dark red and built for long, steady cruising across open water. The moment a swordfish spots a target, it switches from cruising muscle to burst muscle in an instant, the same way a sprinter explodes off the starting blocks. That switch is where the real danger begins. Unlike many ocean predators, a swordfish almost never hunts as part of a group. There is no pack, no team, no backup waiting nearby if something goes wrong. Every hunt happens alone, which means every choice about when to strike and what to strike belongs to a single fish making a split-second decision in open water. That kind of solo hunting only works if the animal making the choice is fast enough and confident enough to trust its own instincts completely. Most people picture swordfish snapping up small fish near the surface, and sometimes that happens. The biggest, boldest meals a swordfish chases live somewhere far stranger, somewhere deeper, somewhere darker. A grown swordfish can weigh over 600 pounds and stretch longer than a small car, yet it regularly leaves the sunlit surface behind to chase prey that most ocean animals never encounter and never survive meeting. What waits down there is not always a smaller fish. In certain parts of the ocean, swordfish have turned up carrying marks from a fight against something far bigger than themselves, something with arms instead of fins and a strength that has nothing to do with speed. We will get to that fight. First, you need to understand the weapon this fish carries into it, because a swordfish is not fast for no reason. That long, flat blade jutting out from its face is a genuine weapon, carried for millions of years and built to end fights before they even start. Sailors from centuries ago learned that the hard way. Old ship logs describe crews finding a sword-shaped weapon buried deep inside the wooden hull of their own boat, driven there by an animal that most likely never meant to attack a ship at all. It simply struck at the wrong moment, at full speed, and never managed to pull free. That bill punched through planks built to survive ocean storms. Now imagine what it can do to something made only of flesh and muscle. In the next chapter, we look closer at that weapon, and why a single piece of bone shaped like a blade might be the most effective hunting tool found anywhere in the entire ocean. Picture a blade longer than your arm, growing straight out of a fish's face. That is the swordfish's bill, and it is not decoration. It can stretch more than 4 feet on a large adult, and can make up nearly a third of the animal's entire body length. Unlike a knife, nobody ever sharpens it. Nobody needs to. The bill is stiff, flattened, and strong enough to slash through a crowd of prey without slowing the fish down at all. Here is how the attack works. A swordfish does not gently pick off one fish at a time like a bird plucking berries. It drives straight into a tight school of prey at full speed, then whips its head side to side like someone swinging a bat through a crowd. Every pass stuns or injures several fish at once. Then the swordfish circles back, calm and unhurried, and eats what is left behind. It hunts like a machine, clearing a room in one violent motion, then walking back through to collect the pieces. This only works because of how the bill is shaped. It is flat rather than round, almost like the blade of a paddle, which cuts drag through the water and lets the fish move faster than a rounder snout ever could. Scientists who study its shape found something else surprising too. The bill barely changes how fast the fish swims at all. It is not there to help the swordfish go faster. It is there purely as a weapon, evolved for one purpose alone. Swordfish do not have teeth built for chewing, so this weapon carries almost the entire hunting job by itself. No teeth, no claws, no venom, just speed and a blade. Compare that to almost any other large ocean predator. A shark relies on rows of replaceable teeth. An orca relies on raw bite force and teamwork. A swordfish relies on a single fixed weapon that never grows back if it breaks, and a single moment of committed violence rather than a prolonged chase. There is very little room for a second attempt once that first strike misses its mark, which makes every hunt closer to a gamble than a guarantee. Now picture that blade meeting something far bigger than a school of mackerel. There is a story sailors told long before modern science ever studied a swordfish, back in the early 1600s. A ship's crew heard a violent crash against their hull in open water, loud enough that nobody understood what had happened. When they later hauled the vessel in for repair, they found a long pointed weapon jammed straight through 3 separate planks of solid wood, still lodged there like a spear thrown by an unseen enemy. It looked, they wrote, like something carved from an elephant tusk. In truth, it was a swordfish bill driven in during a single desperate strike, likely aimed at something the fish mistook for a threat or a meal in the dark. Wood built to survive ocean storms should not fail against a fish. This one did. If a piece of bone can punch through a ship's hull without even trying, it raises an uncomfortable question. What happens when that same bill strikes something alive? Something with no wooden planks to slow it down at all? To answer that, we need to follow the swordfish away from the surface, down past the sunlight, into the part of the ocean where its most dangerous hunts actually happen. The light disappears first. As a swordfish dives, the warm blue water above fades into something colder and darker with every 100 feet. By 600 feet down, sunlight barely reaches at all. By 2,000 feet, it is gone completely. This is where a hunting swordfish spends much of its day, far below where most people ever imagine an ocean predator living. Scientists call this stretch of ocean the twilight zone, and the name fits. It sits below the sunny surface layer where snorkelers swim, and above the crushing pitch-black depths where almost nothing lives at all. Picture the Empire State Building standing on its side underwater. The twilight zone would swallow it more than 4 times over before you ever reach the bottom of its range. It is an enormous, cold, mostly empty stretch of water, and swordfish cross through it constantly, hunting during daylight hours when the surface feels too exposed and too bright. Temperatures drop fast down here too, sometimes by 20 degrees or more compared to the surface above. Most fish slow down in cold water the same way a phone battery drains faster in the cold. Muscles react slower. Eyes struggle to process fading light. Reaction time falls apart exactly when a hunter needs it most. A swordfish does not simply sink down here once and stay. Many spend their daylight hours diving deep into this cold, dark layer to hunt, then rise back toward warmer surface water once night falls, following the very same rising tide of prey animals that migrate upward after dark. This means a single swordfish might cross through a temperature change of 20 degrees or more, twice in a single day, treating a shift that would exhaust most animals as a normal part of its daily routine. A swordfish should suffer the same problem. It is cold-blooded after all, meaning its body temperature normally matches the water around it. By every normal rule of biology, a swordfish diving into cold, dark water should turn sluggish and half-blind, the same as almost any other fish would. Other large ocean hunters that stay closer to the surface, like many species of tuna, never need to solve this particular problem at all, since they simply avoid the coldest, darkest water in the first place. It does not. Something inside this fish breaks the normal rules entirely, letting it hunt with sharp vision and fast reflexes in conditions that should shut both down. Whatever that advantage is, it explains how a swordfish can chase down prey in near total darkness, thousands of feet below the surface, while colder-blooded animals around it struggle just to react in time. That advantage is not luck, and it is not simple toughness either. It comes from one of the strangest pieces of biology found anywhere in the ocean, a built-in heating system growing right behind the swordfish's own eyes, quietly doing a job no ordinary fish organ was ever supposed to do. Understanding that system is the key to understanding everything that happens next in this story. Because the same advantage that lets a swordfish hunt mackerel in the dark is exactly what makes it dangerous enough to challenge something much, much bigger. Behind a swordfish's eyes sits something that should not exist in a cold-blooded animal at all. A heater. Most fish take on the temperature of the water around them completely. Swim into cold water, and a normal fish's whole body cools right along with it, brain included. Thinking, reacting, and seeing all slow down together, the same way an old phone battery drains faster once the weather turns cold. For a hunter chasing fast-moving prey, that kind of slowdown can mean the difference between a meal and going hungry. Swordfish found a workaround. Tucked behind their eyes, connected to muscles that once helped move the eyeball itself, sits a specialized organ built for one job only, producing heat. Scientists call it cranial endothermy, which sounds complicated, but the idea is simple. Picture a tiny space heater running constantly right behind your eyes, keeping them warm even while the rest of your body sits in freezing water. This organ can raise the temperature around a swordfish's eyes and brain by as much as 15 degrees above the surrounding ocean. Nothing else in its body gets that treatment, just the eyes and the brain sitting right behind them, kept warm and sharp no matter how cold the water gets. Scientists only discovered how this organ actually worked by studying it under a microscope. The tissue looks almost like ordinary muscle, packed full of tiny structures normally used to help an eye move and focus. Somewhere along the way, evolution repurposed that same tissue for an entirely different job, burning energy constantly to generate warmth instead of movement. It is a strange kind of biological recycling, taking a part built for one purpose and turning it into something built for a completely different one. Why only those two parts? Because vision and reaction speed are exactly what a hunter needs most in the split second before an attack. A swordfish diving 1,000 feet down does not need warm fins or a warm stomach. It needs eyes that track movement instantly, and a brain that reacts before the moment passes. Everything else about the body can slow down. Those two things cannot. Think of it like a race car idling at a stoplight in freezing weather. The whole car sits cold, engine included, except for one small section the driver keeps heated and ready, so that when the light turns green, there is no delay at all. That is what a swordfish carries into deep water. A body mostly running cold, and a mind kept burning hot, always ready. This single adaptation turns the swordfish into one of the only fast, sharp-eyed hunters, willing to operate in the darkest, coldest layers of the open ocean. Down here, most animals either move slowly or avoid the area completely. A swordfish does neither. It hunts here on purpose, using an advantage almost nothing else in these waters can match. That advantage matters more than it might seem, because the twilight zone is far from empty. It is crowded with strange, half-seen shapes drifting through the dark, creatures built for a world with no sunlight at all, and one of them grows large enough to make even a warm-eyed, fast-reacting swordfish think twice. Turn off every light in your house at once. Then imagine that darkness stretching for miles in every direction. That is an average night in the twilight zone, except this darkness holds thousands of living things drifting through it. Every evening, an event happens here that scientists consider one of the largest movements of life anywhere on the planet. Billions of small fish, shrimp, and other creatures rise up from the twilight zone toward the surface under cover of darkness, feed through the night, then sink back down before sunrise. Scientists call it the daily vertical migration, and it happens every single night, all over the world's oceans, largely unnoticed by anyone standing on shore. A swordfish times its hunts around this rhythm. As the light fades and that rising wave of prey moves upward, a swordfish often follows, cutting through the crowd with its blade while temperatures and darkness barely slow it down at all. Then, as morning approaches and the prey sinks back into deeper water to hide from surface predators, many swordfish follow that retreat too, diving back into the cold and the dark to keep hunting through daylight hours instead of resting. But prey is not the only thing living in these waters. Scattered through the twilight zone are creatures built specifically for permanent darkness, animals that spend their entire lives below where sunlight has ever reached. Many produce their own light, tiny flashes and glowing patches scattered across their bodies like stars scattered across a night sky. Scientists call this bioluminescence, and down here it serves as everything from a hunting lure to a warning sign to a way of finding a mate in a world with no other light at all. Most of these glowing creatures are small, some fit in the palm of your hand. Small lanternfish flicker along their bellies, to break up their own outline from below, hiding their silhouette from anything hunting upward toward the dim light still filtering down from the surface. Other creatures flash bright bursts of light only when startled, using the sudden flare to confuse or blind whatever just grabbed them, buying half a second to escape. But size in the Twilight Zone does not always follow the pattern you would expect. In a place built almost entirely around staying hidden, a few animals took the opposite approach completely. Instead of staying small and blending into the dark, they grew enormous, using size itself as a kind of armor against nearly everything else living down here. One of those animals grows large enough to stretch the length of a school bus, with arms lined in hundreds of sharp-toothed suckers and eyes built bigger than almost any eyes found anywhere in the animal kingdom. For centuries, most people assumed this creature was pure myth, a sailor's tale exaggerated over generations of retelling around a ship's deck. It is not a myth. It is real. It is enormous. And it shares this same dark stretch of ocean with the fast, warm-eyed swordfish we have been following since Chapter 1. Nobody can properly understand a hunt this strange without meeting both animals involved. It is time to meet it directly. Somewhere below 2,000 feet, something drifts through the dark that outweighs a small car. This is the giant squid, and almost everything about it sounds exaggerated until you check the numbers. A full-grown female can stretch nearly 43 feet from the tip of her mantle to the end of her longest feeding tentacles, roughly the length of 2 school buses parked end to end. Some recorded specimens have reached length closer to 60 feet total. It carries 8 muscular arms lined with rows of sharp-edged suckers, plus 2 much longer feeding tentacles tipped with serrated rings, built to grip and hold prey that tries to fight back. For most of human history, almost nobody believed this animal actually existed. Stories of a sea monster capable of dragging entire ships underwater got passed down for centuries, shrinking and growing with each retelling, until most people assumed the whole thing was invented. Old sailors called it the Kraken and treated it as legend, the same category as mermaids or sea serpents. Even scientists dismissed early reports for decades, assuming exhausted or frightened sailors had simply mistaken a large piece of driftwood or an unusual wave pattern for something alive. Modern science eventually proved the legend had a real animal underneath it, even if the ship-dragging part was exaggerated. Its proper scientific name is Architeuthis dux, and it lives in every ocean on Earth, almost always far too deep for people to ever encounter one alive. Nearly everything scientists know about giant squid comes from dead bodies that washed ashore or turned up tangled in fishing nets, since almost nobody has ever filmed one moving freely through open water in its own habitat. The first confirmed footage of a live giant squid in its natural deep-sea home did not arrive until the early 2000s, centuries after sailors first began describing it. Before that moment, an animal this large had somehow managed to stay almost completely hidden from an entire species obsessed with exploring every corner of its own planet. That alone tells you something about how good this creature is at avoiding attention. Despite its size, a giant squid moves through its dark world with surprising precision. Its body has no bones at all, letting it bend, twist and squeeze through gaps that would stop a rigid animal completely. When it needs to escape danger, it can fire a jet of water backward and rocket away far faster than something its size should be able to move. Here is where the story gets stranger though. An animal this large, carrying arms this dangerous, still spends most of its life trying to avoid being seen at all. Everything about its body, the size, the arms, even its skin, developed as a response to threat rather than as a tool for confident hunting. Something out there in the dark has always mattered more to a giant squid than anything it might catch to eat. To understand what that threat actually is, look first at the single strangest feature found anywhere on the giant squid's entire body: its eyes. A giant squid's eye can grow larger than a dinner plate, and scientists believe that size exists for one specific reason. Each eye can stretch up to 10 inches across, making it the largest eye found on any animal on Earth outside of its close relative, the colossal squid. For comparison, a blue whale, the single largest animal that has ever lived on this planet, has an eye only about 6 inches wide. A giant squid, despite weighing a tiny fraction of what a blue whale weighs, carries an eye nearly twice as large. That is a strange trade for evolution to make. Big eyes cost energy to grow and maintain, and in most animals, eye size roughly matches body size and typical prey size. A giant squid's main food source is mostly modest-sized fish and other squid, nothing that would obviously require basketball-sized vision to hunt successfully. Researchers studying this mismatch landed on a different explanation entirely. These massive eyes did not evolve to help the squid find its next meal. They evolved to help the squid spot something enormous moving toward it through total darkness, from as far away as possible, giving it every extra second to escape before the moment turned fatal. Down at these depths, sunlight cannot reach at all, but the water is far from perfectly black. Countless tiny creatures produce faint traces of bioluminescent light as they move, and a very large approaching animal can disturb enough of these glowing organisms to create a dim, shifting outline against the darkness, almost like watching a shadow move across a wall lit by candlelight. A giant squid's enormous eyes are tuned specifically to catch that kind of faint, distant disturbance, sometimes from well over 100 yards away, long before a smaller eye could ever detect it. A smaller squid swimming the same depths might not notice danger until it is only a few body lengths away, leaving almost no time to react at all. Researchers tested this idea using detailed mathematical models, calculating exactly how much extra warning time a 10-inch eye provides compared to a smaller one. Their models showed diminishing returns for spotting small, close objects like typical prey, but a huge lasting advantage for spotting one very specific kind of target, something enormous, moving steadily, and still far enough away to escape from if the squid reacts quickly enough. That kind of range only matters if something out there is both massive and dangerous enough to justify the warning system. And for a very long time, scientists believed exactly one animal fit that description. Everything about the giant squid's body, its size, its ink, its speed, even those extraordinary eyes, appears to have developed as a response to a single natural enemy. Not a fish, not a shark. Something else entirely, an animal so large and so relentless that an entire species spent millions of years evolving basketball-sized eyes just to see it coming from a safe distance. We will get to that famous rival very soon. First, there is something the giant squid's own story tends to leave out completely. A second predator nobody expected to find scars from at all, hiding in plain sight the entire time. Ask almost anyone what hunts a giant squid, and you will get the same answer every time. The sperm whale. That story has circulated for generations and for good reason. Sperm whales dive to the same crushing depths where giant squid live, and scientists have found squid beaks by the thousands sitting undigested inside sperm whale stomachs, proof of just how often this hunt actually happens. Whale skin recovered from these deep divers frequently carries circular sucker scars scattered across the body, physical evidence of a giant squid fighting back hard before losing the encounter completely. For decades, this felt like the entire story. One massive predator, one massive prey animal, locked into a single ancient rivalry playing out again and again in total darkness. Scientists studying the giant squid's oversized eyes assumed sperm whales were the whole explanation, the one threat worth evolving basketball-sized vision to detect from over 100 yards away. Sperm whales themselves seem built specifically for this hunt. They can dive close to 2 miles down, holding their breath for well over an hour at a time, tracking prey through complete darkness using clicks of sound rather than eyesight at all. A sperm whale locates a giant squid the same way a submarine locates another vessel, by listening for the echo bouncing back off a body hidden somewhere in the black water ahead. Against a hunter that does not even need to see its target, a giant squid's eyes would seem almost pointless, which only made the size of those eyes an even stranger puzzle for researchers to explain. Then researchers started finding something the classic story never accounted for at all. Scars matching a giant squid's sucker pattern began turning up on animals that had nothing to do with sperm whales whatsoever. Sharks, patrolling waters nowhere near typical sperm whale hunting grounds, showed up carrying the exact same kind of circular, ringed markings scientists had only ever associated with the whale and squid rivalry. That discovery did not fit the tidy, one predator story everyone had settled on for years. If sharks were tangling with giant squid in the dark, then the sperm whale was never the only large predator willing to test itself against this animal. Something about that idea unsettled the researchers studying it, because sharks and sperm whales hunt in completely different ways, at different speeds, using completely different tools. A shark relies on teeth and raw bite force. A sperm whale relies on size and echolocation to track prey through total darkness. Whatever these scarred sharks had run into clearly did not care which predator showed up looking for a meal. This meant the classic image of one lone whale locked in an ancient rivalry with one giant squid was, at best, only part of a much bigger picture. Giant squid appeared to be a target or perhaps a threat for multiple completely different kinds of predators sharing the same dark waters, with the sperm whale as only one entry on a longer list. And once scientists started looking closer at these unexpected shark scars, one specific encounter, caught almost entirely by accident off the coast of Hawaii, became the piece of evidence that cracked the story wide open. An underwater photographer near Hawaii lifted his camera toward a shark that looked like it had survived a war. The animal was an oceanic white-tip shark, a solid 7 feet long and normally one of the more confident predators cruising these waters. This one was covered along its entire flank in strange circular scars, dotted rings stamped across its skin in patterns nobody swimming nearby had ever seen up close before. Something out there had marked this shark badly, and whatever it was clearly had not gone down without a serious fight. The photograph eventually reached marine researchers, and what they saw stopped them cold. These were not bite marks from another shark, and they were not the kind of scrape a shark might pick up brushing against coral or rock. The rings were too perfectly circular, too evenly spaced, arranged in patterns that pointed toward exactly one kind of animal. Something with arms lined in suckers, and something extremely large. Divers who spend years in these waters see plenty of ordinary shark scars, the kind left by fishing gear, boat propellers, or fights with other sharks over a carcass. This was different enough that experienced local divers immediately flagged it as unusual, passing the photograph along rather than simply filing it away as another routine encounter. Something about the pattern told them this particular shark had a story worth investigating. Researchers narrowed the list of possible suspects down to just 3 animals capable of leaving marks this size in Hawaiian waters. All 3 were massive squid species, including the giant squid itself. Nothing else living in that part of the ocean carries suckers large enough or arms long enough to leave a scar pattern stretching across an entire shark's body, which made the shortlist unusually easy to settle on despite nobody actually witnessing the encounter. What genuinely surprised the research team was the shape of the encounter itself. The scars showed almost no accompanying wounds or tears, the kind of damage you would expect if the shark had been genuinely overpowered and fighting for its life. That absence told its own story. Researchers concluded the shark had most likely been the aggressor here, lunging at the squid rather than the other way around, and the squid had simply fought back hard enough with its arms to leave a lasting mark before the shark broke away. It was, in a strange way, a rare piece of physical proof that a squid this size could hold its ground against an attacking predator without losing the fight entirely. That detail mattered more than it first seemed. It meant something in these waters was confident enough, or perhaps hungry enough, to actually attack a massive squid on purpose, rather than simply being ambushed by one. If a shark was willing to start that fight, one question became impossible to ignore. Was a shark really the only fast, aggressive ocean hunter bold enough to try it? Or was something else out there doing the exact same thing, leaving the exact same kind of scars, somewhere much closer to where fishermen pull their catch straight out of the water? Marine biologists rarely get to study a fight nobody actually witnessed. Usually, all that is left behind is the evidence. That is exactly the position researchers found themselves in after the Hawaii shark photographs began circulating. Nobody had seen the encounter happen. There was no video, no eyewitness account, nothing except a pattern of scars stamped into living skin, left behind by an animal that had already vanished back into deep water long before anyone arrived with a camera. So scientists did what investigators do with any mystery. They studied the evidence itself, piece by piece, treating each scar almost like a signature left at a crime scene. The shape of the rings mattered first. Squid and octopus suckers leave distinct circular marks, completely different from the ragged tears or puncture wounds left by teeth or claws. The spacing between each ring mattered too, since different squid species carry suckers of different sizes, spaced differently along the length of each arm. Even the arrangement told a story, since some squid species carry a single row of suckers running down each arm, while others carry 2 rows running side by side. Researchers examining the Hawaii shark scars ruled out smaller, more common squid species almost immediately. The rings were simply too large, spaced too far apart to match anything typical swimming through those waters. That left only the handful of truly massive squid species capable of producing marks on this scale, animals rarely seen alive and almost never up close. This kind of scar reading is not a new technique either. Scientists studying sperm whale skin have used the exact same method for decades, matching circular scar patterns recovered from whale bodies to specific giant squid arm and tentacle structures, essentially reconstructing details of a fight nobody was ever present to record firsthand. Think of it like a doctor reading an old injury on a patient's body years after the accident happened. The scar itself cannot speak, but its shape, depth, and location still carry real information for anyone trained to read it correctly. A rounded scar tells a different story than a jagged one. A cluster of matching rings tells a different story than a single random mark. Marine biologists apply that same careful reading to an animal's skin, turning silent old wounds into a surprisingly detailed account of an encounter that happened months or even years earlier. What made the Hawaii case different was simply the animal wearing the scars. Nobody expected to find this kind of evidence on a shark. The classic giant squid story only ever mentioned one predator worth fighting, and it was never a shark patrolling relatively shallow coastal waters near a tourist destination. Once researchers accepted that sharks could carry this kind of evidence, an obvious next question followed almost immediately. Sharks were not the only fast predators swimming through waters where giant squid also lived. Somewhere else in the ocean, another animal known for speed and aggression might be carrying the exact same kind of proof if anyone bothered to actually look closely enough to notice it. Someone had already been looking. Not in a research lab, but at a fish market on the coast of Massachusetts. At a fish market on Cape Cod, workers handling swordfish catches started noticing something strange about certain fish coming through, particularly during the colder winter months. Scattered across the swordfish, usually somewhere near the head or along the length of the bill itself, were rings. Circular marks, sometimes overlapping, pressed into the skin in patterns that looked exactly like the sucker scars researchers had already documented on sharks and sperm whales elsewhere. Workers who handled dozens of fish every week began recognizing the pattern almost immediately whenever it turned up. At first, this seemed like nothing more than an odd curiosity worth mentioning between co-workers. Swordfish get scraped and marked all the time, brushing against rocks, other fish, fishing gear, or each other during aggressive encounters. But these particular marks kept a consistency that random scrapes never showed. The rings stayed roughly the same size fish after fish. They stayed roughly the same distance apart, and they kept showing up in the same general area near the mouth, exactly where a fish would carry scars from something that had grabbed onto its bill during a close-range struggle. Workers who had handled swordfish for years, long before anyone connected the marks to squid at all, began keeping a rough mental tally of how often the pattern appeared. Some years it turned up rarely. Other winters, especially when certain squid populations seemed to be more active in nearby waters, the marked fish showed up often enough that it stopped feeling like a coincidence and started feeling like a genuine seasonal pattern worth taking seriously. Online communities of squid researchers and enthusiasts eventually connected with people working these fish markets directly, comparing notes and photographs across completely different parts of the ocean. What they found lined up in an unsettling way. The ring patterns showing up on Atlantic caught swordfish closely matched sucker sizes belonging to large squid species known to live in exactly those Atlantic waters. A single strange fish would have been easy to dismiss. A repeating pattern, showing up across multiple catches, multiple seasons, and multiple locations along the same general fishing routes, was much harder to explain away. Photographs travelled between amateur researchers and professional scientists alike, each new submission adding one more data point to a picture nobody had set out to build in the first place. One detail stood out above the rest. The clearest, most obvious ring pattern anyone documented appeared close to the swordfish's mouth, exactly the spot you would expect scarring to appear if a squid's arm had wrapped tightly around the base of the bill during a violent, close-range struggle rather than a passing brush against something in open water. This raised an important question that a single scar alone cannot answer. Coincidence can explain one strange mark on one fish. It struggles to explain the same mark in the same location, showing up again and again across an entire fishing season, year after year, on fish pulled from the same general stretch of ocean. To settle that question, researchers needed a way to read these scars with more precision than a rough visual comparison, treating each ring almost like a fingerprint left behind at the scene of an actual fight. A fingerprint left at a crime scene can name a suspect nobody actually witnessed committing the act. A scar left on a swordfish works almost exactly the same way. Every squid species carries suckers built slightly differently from every other species. Some carry a single row of suckers running down the length of each arm. Others carry 2 rows, running side by side like a zipper. Some suckers sit close together in tight, even spacing. Others sit farther apart, occasionally on tiny stalks that leave a slightly different mark than a flat sucker pressed directly against skin. None of these differences are obvious at a glance, but together they work almost like a signature unique to each species. Researchers examining scarred swordfish specimens started measuring these details carefully. Ring diameter came first, since larger suckers naturally belong to larger, older squid. Spacing between each ring came next, revealing whether the attacking animal had a single row of arm suckers gripping the fish, or a more complex double-row pattern. Some markings even showed faint secondary rings sitting just beneath the main pattern, suggesting the squid involved carried more than one row of gripping structures working together during the struggle. Piece all of that together, and a blurry ring pattern on a fish's skin starts turning into something closer to an actual identification. One especially clear specimen showed rings with sharp, defined tooth marks near each ring's edge, running vertically along the fish's body close to the mouth, features researchers matched confidently to a genuine giant squid encounter rather than a smaller, more common species passing through the same waters. Not every scar tells such a clear story though. Some markings arrive faded, overlapping, or partially healed, making a confident identification much harder. In those cases, researchers can usually still narrow the list down to a small handful of possible squid species based on general size alone, even if pinning down the exact species proves impossible. An incomplete fingerprint still rules out plenty of suspects, even without naming the one responsible. A healed scar might blur its edges over time, but the overall size and spacing of the pattern tends to survive long after the wound itself has closed. This method is not guesswork built entirely from imagination either. It follows the exact same approach scientists have used for decades studying sperm whale scars, where sucker ring measurements taken from whale skin have been matched successfully to specific squid species based on published records of typical sucker size and arm structure. If the method works reliably enough to identify a squid species from a whale's skin, there is no clear reason it should stop working simply because the animal wearing the scar happens to be a fish instead of a much larger mammal. Once this identification method proved reliable, researchers and enthusiasts comparing photographs from different fishing regions noticed something that made the entire mystery feel much bigger than one unusual fish market on the American coast. The same style of scarring, matching the same general squid characteristics, had also turned up on swordfish caught on the completely opposite side of the planet in the Pacific Ocean, thousands of miles from Cape Cod. 2 fishing crews working oceans apart pulled in swordfish carrying nearly identical scars, and neither one had any idea the other catch existed. One set of markings came from the Atlantic, off the northeastern coast of the United States, examined closely by workers at a small Cape Cod fish market who had grown familiar with the pattern over several winters. The other came from swordfish caught thousands of miles away in the Pacific Ocean, examined independently by a completely different group of people with no connection to the Atlantic findings at all. When photographs from both regions eventually landed side by side for comparison, researchers noticed the ring patterns lined up closely enough to raise real questions. Some of the Pacific specimens carried scars slightly smaller in diameter, suggesting a somewhat smaller squid species had been responsible in those particular cases, something large but perhaps not reaching full giant squid size. Still, the basic pattern matched. Circular rings, consistent spacing, same general location near the fish's head and mouth. One especially interesting wrinkle came from workers at that same Cape Cod market. For years they had assumed every swordfish passing through their shop was caught locally in the Atlantic. After studying the ring patterns more closely and comparing them against known squid ranges, they started suspecting some of their supposedly Atlantic-caught fish might have actually originated somewhere in the Pacific instead, carrying scars from a squid species that simply does not live in Atlantic waters at all. A detail buried in a fish's skin ended up quietly raising questions about where their seafood was actually coming from in the first place. Step back from the individual scars for a moment, and the bigger picture becomes hard to ignore. A repeating pattern, showing up across multiple oceans, multiple fishing seasons, and multiple independent groups of people who had no reason to coordinate their findings with each other, points to something far bigger than one strange fish caught once in unusual circumstances. Whatever these swordfish are running into out in open water is happening often enough, in enough different places, to leave a consistent, recognizable mark behind. Consider how unlikely that consistency actually is. Two oceans separated by an entire continent, two completely different squid populations, and two groups of fishing workers who had never spoken to one another, all documenting nearly identical evidence without knowing anyone else had noticed the same thing. A pattern that stubborn rarely turns out to be random chance. Once enough independent observations line up this closely, and it left researchers with a genuinely global mystery rather than one isolated regional curiosity. That consistency forces an uncomfortable question to the surface. If a fast, aggressive predator like a swordfish keeps ending up scarred by something with arms and suckers, is it actually winning these encounters, or is it simply the one surviving to swim back into a fisherman's net afterward? Somewhere out there, in waters where nobody was filming and nobody was watching, a giant squid weighing hundreds of pounds and a swordfish built for speed collided in total darkness. Only one side of that story keeps showing up on land, carried home in the hull of a fishing boat. Put a giant squid and a swordfish side by side on paper, and the matchup looks almost impossible to call. A large adult giant squid can weigh several hundred pounds, with some estimates for the biggest specimens climbing even higher, its body built entirely around 8 muscular arms and 2 long tentacles capable of gripping and holding onto prey that tries to fight back. A large adult swordfish can weigh over 1,000 pounds itself, sometimes even more, built around raw speed, a bladed weapon, and almost nothing in the way of natural defences beyond simply outrunning trouble. On paper, these numbers alone do not settle much of anything. Depending on the specific animals involved, either one could genuinely outweigh the other. Size is not really the deciding factor here at all, and that fact alone should surprise you. Length adds another wrinkle to the comparison. Much of a giant squid's total length comes from its 2 long feeding tentacles, thin and flexible rather than solid muscle from tip to tip. A swordfish, by contrast, carries most of its length as dense, powerful muscle built entirely for propulsion. Two animals can measure roughly the same on a tape and still be built for almost completely different kinds of combat, which makes any simple size comparison between them somewhat misleading from the very start. In most animal matchups, bigger usually wins. A larger predator typically overpowers a smaller one through sheer strength, and prey animals typically survive an attack by simply being too large or too tough to bring down easily. This particular rivalry breaks that pattern almost completely. A giant squid brings raw grip strength, 8 arms working together, and a beak sharp enough to tear through tough material with ease. A swordfish brings something that arm strength alone cannot easily counter, a bladed weapon moving at extremely high speed, striking before the squid ever gets a full grip established in the first place. Speed changes the entire calculation. A slow, powerful animal loses most of its advantage the moment a faster opponent lands a decisive hit before any real grappling ever begins. Think about it like a heavyweight boxer facing off against a much faster opponent who simply refuses to get close enough for a grab or a hold. Strength matters far less when the other fighter never lets the fight happen on the strong fighter's terms. That is roughly the situation a giant squid faces against a hunting swordfish. All that grip strength, all those suckers and that powerful beak mean far less if the swordfish's bill strikes hard and fast before the squid can wrap even a single arm around it. But the moment that first strike fails to land cleanly, or fails to land at all, the entire balance of the fight can flip immediately, handing every advantage straight back to the squid. Understanding exactly how that first strike works, and exactly why it sometimes fails, means looking closely at the two actual weapons involved in this fight. A bill built from bone, and a beak built from something almost harder to believe. Two ancient weapons, one bone, and one built from something else entirely, meet somewhere in total darkness. The swordfish brings its bill, the same flattened, blade-shaped weapon capable of punching clean through solid wooden ship planks. It has spent millions of years being refined for exactly one purpose: delivering a fast, slashing strike capable of stunning or killing prey in a single pass, before that prey ever gets a chance to react or fight back. The giant squid brings something almost stranger. Sitting at the centre of its 8 powerful arms is a beak, shaped remarkably similar to a parrot's beak, except built from one of the hardest, toughest materials found anywhere in nature. This beak is strong enough to tear straight through thick fish scales, crab shells, and the tough cartilage found in smaller sharks, all without a single bone anywhere in the squid's entire body to brace against while biting down. Scientists studying this material have found it tough enough that engineers now study its structure for ideas on building better body armour and protective equipment for humans. What makes the beak so unusual is how it transitions from soft to hard across a very short distance. The base, where it connects to the squid's soft muscular body, stays flexible enough to avoid tearing the surrounding tissue with every bite. The tip, doing the actual cutting, hardens into something almost as tough as certain metals. Very few materials found anywhere in nature manage that kind of transition, soft on one end and remarkably hard on the other, within the space of just a few inches. Here is what makes this fight genuinely different from most predator encounters happening anywhere else in the ocean. Both animals bring a weapon capable of seriously hurting or killing the other, which puts them closer to two armed opponents meeting in a pitch-black room than to a dangerous hunter facing down mostly defenseless prey. Each is fully capable of ending the fight in a single well-placed strike, and neither one is able to clearly see exactly where the other one is standing. That last detail changes everything. In full daylight, an animal with sharper vision usually gets a clear advantage, watching an opponent's movements and reacting accordingly. Down here, past 2,000 feet, there is no daylight left at all. The only real light comes from occasional bioluminescent flickers, drifting through the water, faint and unreliable at best. Neither animal gets to clearly watch the other approaching from any real distance. This is exactly where the swordfish's strange advantage from earlier chapters becomes so important. Remember that heater organ, quietly warming the swordfish's eyes and brain while the rest of its body sits cold? In a fight decided almost entirely by which animal reacts first in near total darkness, warm eyes and a fast-reacting brain matter more than almost anything else involved. A giant squid, despite its massive size and those famous basketball-sized eyes, still relies on cold-blooded reflexes running at whatever speed the surrounding freezing water allows. 2 dangerous weapons, 1 dark arena, and a fight where the winner might come down to a fraction of a second nobody down there was ever built to measure. That fraction of a second is exactly what decides the outcome. In total darkness, being bigger stops mattering nearly as much as being faster. That single fact flips almost everything you would normally expect from a fight this size. Picture 2 boxers thrown into a completely dark room, unable to see each other at all, forced to rely purely on hearing and instinct to land a hit. The bigger fighter's raw strength counts for very little if he cannot locate his opponent quickly enough to actually use it. The faster, sharper reacting fighter, even a smaller one, gets a real advantage simply by finding his target first and committing to the strike without hesitation. That is roughly the situation playing out between a hunting swordfish and a giant squid somewhere below 2,000 feet. Remember that heater organ from a few chapters back, quietly keeping the swordfish's eyes and brain running warm while the rest of its body matches the freezing water around it. That warmth becomes the deciding advantage down here. While a giant squid's massive eyes gather every scrap of available light extremely well, its actual reaction speed still depends on cold-blooded muscles and nerves running at whatever pace the surrounding freezing temperature allows. A swordfish fighting in the exact same freezing water keeps its most critical systems' vision and reaction time running as if it were still swimming through comfortable sunlit surface water. This gap does not need to be large to matter enormously. In a fight decided by whichever animal strikes first, even a small reaction time advantage, a fraction of a second faster to spot movement and commit to an attack, can decide the entire outcome before the slower animal ever finishes reacting to the threat at all. A swordfish attacking in this environment almost certainly commits to one single decisive strike rather than a drawn-out struggle. Circling back for a second attempt against an animal capable of gripping tight enough to hold a struggling fish in place would give the squid exactly the opening it needs, a chance to wrap multiple arms around the fish and bring its beak into direct contact. Every advantage the swordfish holds exists specifically in that first, fast, committed strike. Everything after that first strike favours the squid instead. This explains something that puzzled researchers examining scarred swordfish specimens for years. Some fish carried scars but showed no sign of a fatal wound anywhere on their body, meaning the fish clearly survived whatever encounter left those marks behind. Other evidence suggested some fights ended very differently for the fish involved, with far more serious damage left behind. Reaction speed like this cannot be trained or improved over a lifetime either. It comes built in from birth, wired directly into the swordfish's biology long before it ever encounters anything worth fighting. A young swordfish carries the same warm-eyed advantage as an old one, meaning even a first-time encounter with a giant squid does not leave the fish fumbling through unfamiliar territory the way an inexperienced hunter normally might. Speed alone does not guarantee victory here, though. Even facing a faster, warm-eyed opponent, a giant squid is far from helpless the moment a fight actually begins. It carries one final option most people never picture when they imagine a fight this size, a defense mechanism far older than any of the weapons already discussed. When everything else fails, a giant squid still has one last option. It disappears. Deep in its mantle sits an ink sac connected to a gland capable of producing a thick, dark cloud on demand. The moment a giant squid senses real danger, whether from a swordfish's bill, a shark's teeth, or a sperm whale closing in through the dark, it can release that ink directly into the surrounding water in an instant. Down at these crushing depths, where almost no natural light exists in the first place, a cloud of ink spreading through already dark water works even better than it would near the sunlit surface, turning an already dim environment completely blind for anything nearby. That cloud buys time, and a giant squid uses every second of it. The same powerful mantle muscles that help it swim also let it fire a strong jet of water backward, launching the animal away from danger at a burst of speed. Most people would never expect from something this size. Combine the ink cloud with that sudden burst of speed, and a giant squid can vanish from a fight almost as suddenly as it appeared in the first place, leaving behind nothing except drifting dark water and possibly a torn arm or two. This defense explains something important about the encounters researchers have pieced together through scar evidence. Many of the marked animals studied, whether sharks or swordfish, showed scars consistent with a squid that had gripped on briefly during a struggle, then broken free rather than being fully overpowered and consumed. An ink cloud followed by a fast retreat gives a giant squid exactly the kind of opening it needs to survive an encounter with a faster, better-armed opponent, even after that opponent has already landed the first serious strike. Consider what this means for a hunting swordfish. Even a fast, precise, perfectly aimed strike does not guarantee an easy meal. The moment that first hit lands, and if it fails to be immediately fatal, the swordfish now faces a sudden wall of ink and a target actively working to disappear into darkness that already favoured hiding in the first place. Everything about this fight, the timing, the environment, the weapons involved, comes down to a series of fractions of a second stacked one after another, with almost no room for a second attempt if the first one goes wrong. The ink itself carries one more trick worth knowing. Some squid species release ink shaped into a rough blob roughly the same size as their own body. A decoy built to hang in the water and absorb an attacker's strike while the real squid jets away in a completely different direction. Whether giant squid use this exact trick remains unconfirmed, since so few encounters have ever been observed directly, but close relatives are known to rely on it regularly, when survival depends on buying just one extra second. Most of what has been described so far comes from indirect evidence. Scars, scarred sharks, marked swordfish, broken bills, pieced together clues from animals that survived to be caught, examined and studied on land, long after their actual encounter had already ended in total darkness, far from any human witness. That is about to change. Because at least once, almost entirely by accident, something managed to catch a piece of this fight directly on camera. A giant squid has no skeleton at all, and that changes everything about what a losing fight looks like. Most large ocean predators carry some kind of internal frame, a set of bones or cartilage that protects vital organs from a direct hit. A shark has cartilage running the length of its body. A whale has a full skeleton wrapped in thick blubber. A giant squid has none of that. Its entire body is soft tissue, muscle, and a thin internal structure called a gladius, essentially a flexible support rod running through the mantle that gives the body some shape without offering much real protection at all. This soft design works well for squeezing through gaps and moving with incredible flexibility. It becomes a serious weakness the moment something fast and armed finds an opening. A swordfish bill does not need to punch through bone to reach something vital. A single accurate strike through the mantle, where the squid's heart and other organs sit unprotected, could end the fight in one motion, with almost nothing standing between the blade and the damage it causes. Compare this to almost any bony fish the swordfish might otherwise hunt. A mackerel or a small tuna carries a spine and a rib cage, providing at least some structure capable of deflecting a glancing blow before it reaches something critical. A giant squid offers no such buffer anywhere on its entire body. The mantle itself is where the real danger concentrates. This muscular tube houses the squid's 3 hearts, its gills, and the jet propulsion system it depends on for both hunting and escaping. Damage to this single area threatens almost every system the animal needs to survive. Compare that to a swordfish, whose vital organs sit protected somewhere within a dense muscular body built for absorbing impact during high-speed collisions with prey. The squid carries no equivalent protection anywhere. This imbalance explains why a losing encounter for a giant squid often ends far worse than a losing encounter for the swordfish attacking it. A swordfish that misses its strike or lands a glancing hit typically swims away with only minor damage. A giant squid struck cleanly through the mantle may not get the chance to swim away at all. Even a survivable hit carries lasting consequences. Torn or severed arms do not simply grow back overnight, leaving an injured squid with reduced hunting ability and weaker defences against whatever predator finds it next. A wounded giant squid trailing torn tissue and leaking fluid becomes an easier target for every other hunter cruising through the same dark water, turning one narrow escape into a much longer, more dangerous struggle to survive. Blood and torn tissue drifting through open water rarely stays private for long either. Scent and faint vibrations travel surprisingly far through cold, dense seawater, and other predators patrolling the same general depth can pick up on exactly this kind of signal from a genuine distance. A wounded giant squid may face a second unrelated threat within hours, arriving specifically because something struggling is now broadcasting its location to anything nearby. None of this happens in front of witnesses. Every detail described here comes from piecing together injuries found on dead or stranded animals, examined long after any actual struggle has ended. For decades, that indirect evidence was the closest anyone could get to understanding this rivalry at all. That changed, at least partly, the moment researchers finally managed to point a working camera into the right patch of dark water at exactly the right moment. For more than a century, catching a live giant squid on camera stood as one of the greatest unsolved challenges in wildlife filmmaking. Every previous attempt had failed completely. Submersibles descended into the darkness carrying bright lights and loud equipment, hoping to spot something the size of a school bus drifting past. Every single time the ocean stayed empty, or the squid simply avoided the noise and light long before any camera could capture it. Researchers began to wonder whether filming this animal alive in its own natural habitat might actually be impossible. One team took a different approach entirely. Instead of searching randomly through open ocean, Japanese researchers studied where sperm whales gathered to feed each year in the Western Pacific, reasoning that the whales themselves were far better at finding giant squid than any human equipped with cameras and lights ever could be. If a hungry sperm whale kept returning to the same patch of deep water, something worth eating was almost certainly living down there. This idea sounds simple once explained, but putting it into practice took years of patient tracking. Researchers followed individual whales for entire feeding seasons, noting exactly where each animal dove and how long it stayed submerged before surfacing again. Slowly, a map began forming, marking specific stretches of deep water that whales visited again and again, season after season, far more consistently than any other patch of ocean nearby. The strategy worked. In 2004, using a specially designed submersible following exactly this method, researchers finally captured a giant squid on camera near this feeding ground, marking the very first confirmed footage of the species in anything resembling its natural environment. 2 years later, the same team managed something even more remarkable, hooking a live giant squid on a fishing line and filming it as it attacked bait near the surface before eventually breaking free. Then, in 2012, a full film crew working with the same research method captured extended footage of a giant squid swimming freely through open water at roughly 2,000 feet down, calm and undisturbed, offering scientists their clearest look yet at how this animal actually moves and hunts when nobody is chasing it. Word of the footage spread fast once it aired publicly the following year, and fishermen working nearby waters described the reaction perfectly. For an entire lifetime, this animal had been treated as half myth, something whispered about at ports and joked about on long fishing trips. Seeing it move calmly through real water in real time turned decades of legend into something undeniably physically real. Scientists studying the footage frame by frame noticed something else worth mentioning too. The squid moved with far more grace and control than most people expected from an animal, so often described using words like monster or beast. Its arms trailed behind it in smooth, coordinated waves rather than the frantic thrashing shown in most dramatic recreations, suggesting an animal built for patient, controlled movement through its environment rather than constant, chaotic violence. That footage proved a giant squid alive and hunting could finally be observed directly. It did not solve the deeper mystery this story keeps circling back to. Nobody, not even with a full film crew and years of patient planning, has ever managed to capture the actual moment a swordfish and a giant squid collide in the dark. Filming a giant squid took researchers a full century of failed attempts. Filming its fight against a swordfish has never happened at all. Part of the problem comes down to simple statistics. Even in waters known for supporting large squid populations, an individual giant squid remains an incredibly rare sight, spread thin across enormous stretches of open ocean thousands of feet deep. Add a second animal, a hunting swordfish, moving independently through that same vast darkness, and the odds of both showing up in the same tiny patch of water at the exact moment a camera happens to be recording shrink close to nothing. Equipment creates its own problem too. Most cameras built for deep-sea filming rely on bright lights to see anything at all in water, with zero natural sunlight. Those same lights, so useful for humans trying to watch, likely warn nearby animals that something unusual has entered their territory. Recent expeditions studying the giant squid's even larger relative, the colossal squid, confirmed exactly this concern. Researchers finally captured that species alive for the first time only very recently, spotting a young individual drifting near the South Sandwich Islands during a research voyage focused mostly on mapping the ocean floor. They noted the animal seemed to actively avoid loud, bright equipment whenever possible, the same equipment nearly every deep-sea camera depends on to function. That colossal squid encounter carried its own reminder about how little researchers still know about these animals. The individual filmed measured barely a foot long, small enough to fit inside a kitchen sink, yet scientists on board immediately recognized it as something significant rather than simply a juvenile too young to matter. Every direct sighting of an animal this elusive, no matter how small or brief, adds genuinely rare information to a research field built almost entirely on second-hand evidence. A swordfish, already alert and hunting with warm, sharp eyes, built specifically to catch fast movement in dim light, would likely notice an approaching light and camera rig even faster than a squid might. That means the exact moment researchers most want to capture, the instant a swordfish commits to its attack, is also the moment least likely to happen anywhere near visible, functioning equipment. This absence of direct footage cuts two different ways depending on how you look at it. Some scientists argue it simply proves how rare and difficult this particular encounter is to witness. Nothing more mysterious than bad luck stacked on top of a genuinely hard filming challenge. Others find something a little more unsettling in the silence. An encounter this violent, happening in a place this dark, this deep, and this far from any human witness, essentially guarantees that almost everything we know comes from indirect evidence alone, pieced together entirely from scars and broken weapons rather than a single clear, undeniable image. That gap between evidence and direct proof becomes even more interesting once you consider a completely different predator sharing these same waters, one whose relationship with the giant squid has been studied far longer and in far greater detail than anything involving a swordfish. Long before anyone suspected a swordfish might challenge a giant squid, scientists had already built an entire body of research around a different, much larger rival, the sperm whale. A full-grown sperm whale dwarfs almost everything else in this story. These animals can stretch past 60 feet long and weigh well over 80,000 pounds, making them 50 to 150 times heavier than even the largest documented giant squid. Unlike the swordfish, a sperm whale does not rely on sharp eyesight to hunt in total darkness. It uses sound instead, producing powerful clicks loud enough to build a detailed acoustic picture of anything moving nearby, essentially working like a living sonar system, capable of locating prey from a significant distance without needing any light at all. That clicking sound ranks among the loudest noises produced by any living animal on Earth. Powerful enough that scientists studying it have questioned whether the sound itself might momentarily stun smaller prey caught directly in its path. A sperm whale hunting a giant squid may not simply be listening for its target, it may be actively softening that target up before the two ever make direct physical contact at all, an advantage no swordfish has ever needed to develop. This hunting method makes sperm whales extraordinarily effective predators of giant squid specifically. A single large whale can consume hundreds of squid across a single year, diving over half a mile down and holding its breath for well over an hour at a time to reach the depths where its prey lives. Scientists studying stranded or hunted sperm whales have recovered thousands of undigested squid beaks from a single stomach, direct physical proof of just how central this prey source is to a whale's entire diet, since these tough, hooked structures pass through digestion almost completely intact. The giant squid does not go down without resistance, though. Whales examined after death frequently carry circular scars scattered across their heads and bodies, physical proof that the squid fought back hard during the final moments of the struggle, wrapping its arms tightly enough around the whale's skin to leave a lasting mark even in a fight it clearly did not win. Older whales often carry so many overlapping scars that individual encounters become impossible to separate, layer stacked on layer across a lifetime spent hunting the same dangerous prey. For generations, this rivalry stood as the single most famous predator relationship in the deep ocean, studied, documented and repeated in nearly every account of the giant squid ever written. It felt complete, a tidy pairing of one massive hunter and one massive prey animal locked in an ancient ongoing struggle, simple enough to explain in a single sentence and dramatic enough to anchor an entire chapter of natural history. Then, researchers looking closely at these whale scars started noticing something that did not quite add up. Compare a scar on a swordfish to a scar on a sperm whale, and you would expect the whale's marks to tell a simpler, more complete story. Scientists have studied this particular rivalry for far longer after all. Instead, the whale scars raised a genuine puzzle. Some of the largest circular marks recorded on old sperm whales measured wider than anything a confirmed giant squid specimen should reasonably be able to produce, based on known sucker sizes recorded from actual captured animals. A few researchers suggested a simple explanation. As a young whale grows larger over its lifetime, scars from an early encounter can stretch along with the surrounding skin, making an old wound left by a smaller squid eventually look far bigger than the animal that originally caused it. That explanation accounts for some of the oversized scars, but not necessarily all of them. Other researchers pointed toward a different possibility entirely. Some of these unusually large marks may actually trace back to a far less studied cousin, the colossal squid, an animal that lives even deeper and carries sharp rotating hooks on its tentacles rather than simple toothed suckers. A colossal squid encounter would leave a noticeably different kind of scar, and at least some old whale specimens appear to show exactly that kind of pattern, mixed in among the more familiar circular rings. The colossal squid itself remained almost entirely theoretical for most of the 20th century, known only from fragments recovered inside whale stomachs rather than any complete specimen. Scientists could estimate its probable size and general shape from these scattered remains, but confirming exactly how large a fully grown individual could get and exactly what kind of scar its hooks might leave behind stayed frustratingly out of reach for decades at a time. This detail matters far more than it might first seem. If some of the deep ocean's most famous predator scars actually come from two completely different squid species, both massive, both poorly understood, and both nearly impossible to observe alive, then the classic whale versus squid story was never quite as simple or complete as it sounded for over a century, no matter how often it got repeated in books and documentaries as settled fact. Apply that same lesson to the swordfish scars examined earlier in this story, and an important question follows naturally. If experienced researchers can still argue over exactly which squid species left a mark on something as heavily studied as a sperm whale, how confident can anyone really be about identifying the exact animal responsible for the far less studied scars found on a swordfish? The honest answer researchers keep arriving at is uncomfortable but simple. Reading a scar correctly narrows down the list of suspects considerably. It rarely closes the case completely, and in the deep ocean, closing a case completely may never really be possible at all. Not every encounter down here ends with the squid losing. Most of the evidence gathered throughout this story focuses on a squid's escape or defeat, since dead or scarred specimens are simply easier to study than a fight still actively unfolding somewhere in the dark. But a giant squid brings real advantages into any confrontation, tools capable of turning a losing position into a genuine standoff, or even flipping the entire fight in its favour. Grip strength sits at the centre of this advantage. Each of the giant squid's 8 arms carries rows of powerful toothed suckers, and its 2 longer feeding tentacles end in serrated rings built specifically to lock onto struggling prey and refuse to let go. If even a few of those arms manage to wrap fully around an attacker before that attacker lands a fatal strike, the fight shifts dramatically. A trapped predator now has to break free from multiple points of contact simultaneously, fighting against a grip built by millions of years of evolution, specifically for holding on under pressure. Consider how differently this changes the calculation for a swordfish already committed to its strike. A miss or a shallow hit no longer simply means swimming away to try again later. It means suddenly finding one or more powerful arms already tightening around the body, each lined with dozens of small, sharp-toothed suckers actively working to keep that grip from slipping. Escaping that hold, especially while still recovering from the effort of a full-speed attack, becomes its own separate struggle entirely. Depth itself becomes a weapon too. A giant squid comfortable at 1,500 feet or deeper can potentially drag a struggling attacker into water that pushes past what that predator normally tolerates, forcing an uncomfortable retreat simply through relentless downward pressure rather than any direct physical strike at all. Smaller sharks documented fighting large squid in shallower coastal waters likely never face this particular danger, but a swordfish encountering a giant squid at its preferred hunting depth faces an opponent perfectly comfortable going even deeper if the fight demands it, turning its own home ground into a genuine tactical advantage. Numbers help the squid as well. While a swordfish typically hunts completely alone, a giant squid's 8 arms function almost like 8 separate weapons working in coordination, each one capable of grabbing, tearing, or holding on independently, while the central beak searches for an opening to strike back. A predator focused on avoiding one arm can easily find a second or third arm closing in from a completely different angle. None of this guarantees victory for the squid in any given encounter, and clear evidence exists on both sides of this rivalry. It does explain why researchers increasingly describe this matchup as a genuine toss-up rather than a predictable, one-sided hunt. Which raises an obvious question. If the outcome stays this uncertain and the danger runs this high, why would a swordfish ever choose to start this fight in the first place? Every dangerous hunt an animal chooses to attempt comes down to a simple, brutal calculation. Does the potential reward outweigh the very real risk of serious injury or death? For a swordfish patrolling the twilight zone, that calculation happens constantly, shaped by exactly how much food is actually available at these extreme depths. Unlike the crowded, resource-rich surface waters most people picture when they imagine ocean life, the twilight zone offers far less food per square mile. Prey here tends to be smaller, more scattered, and harder to locate consistently, forcing any hunter working these depths to think seriously about efficiency rather than simply chasing whatever crosses its path first. Scientists studying energy budgets in large predatory fish often describe this trade-off using a simple idea borrowed from basic economics. Every hunt costs a certain amount of energy just to attempt, whether or not it actually succeeds. A hunter operating in a food-scarce environment needs each successful attempt to pay back significantly more energy than it originally spent, or the entire strategy eventually fails and the animal starves despite constant effort. This pressure only grows stronger the deeper and darker the hunting ground becomes. A giant squid represents an enormous concentration of food in a single location, far more meat in one place than dozens of smaller fish scattered individually across miles of open water. For a swordfish burning enormous amounts of energy, just maintaining its warm eyes and brain in freezing conditions, finding one meal this large could mean the difference between thriving through a difficult season and slowly starving despite constant effort. This kind of calculation shows up throughout the natural world whenever predators face genuinely dangerous prey. Lions occasionally risk serious injury attacking adult buffalo, rather than settling only for easier, smaller targets, because the nutritional reward from one successful buffalo kill can sustain an entire pride for days. A swordfish weighing this same trade-off in the deep ocean faces a similar logic, just played out in darkness rather than daylight, and against an opponent carrying suckers and a beak instead of horns and hooves. Opportunity likely plays a role too, beyond pure hunger alone. A swordfish does not necessarily plan these encounters in advance, deliberately hunting for giant squid the way it hunts smaller, more predictable prey. More likely, these fights happen when a swordfish already moving at speed through dark water suddenly detects movement large enough to represent a serious meal, and its instincts, honed by millions of years of opportunistic hunting, simply take over in that moment. Whether planned or purely opportunistic, the fish committing to this attack faces genuine danger with no guarantee of success. Understanding exactly how large a reward might justify that risk means looking closely at what a giant squid meal is actually worth, measured against everything else available to a hungry swordfish patrolling these same dark waters. Picture emptying an entire refrigerator into your stomach in one sitting. For a swordfish, a single giant squid meal offers something close to that kind of payoff. A large giant squid can weigh several hundred pounds, packed almost entirely with dense, protein-rich muscle tissue built for constant swimming and quick bursts of speed. Compare that to a typical meal a swordfish might otherwise catch, a single mackerel or small squid weighing only a few pounds at most. Successfully bringing down one giant squid could realistically replace dozens, possibly even hundreds, of smaller individual hunts spread out across many separate nights. Think about the same trade-off in more familiar terms. Imagine choosing between hunting down a single large animal, capable of feeding a family for a week, or spending that same week catching just enough small fish to cover a single day at a time, over and over, with no real buffer if a storm or bad luck interrupts the routine even briefly. Once framed that way, the appeal of a single enormous, if dangerous, meal becomes much easier to understand from the swordfish's perspective. That math matters enormously in an environment where hunting itself carries real cost. Every chase burns energy, and every failed attempt means calories spent without any reward gained in return. A swordfish repeatedly chasing small, scattered prey through cold water spends a significant portion of its daily energy simply searching and pursuing, leaving less available for growth, reproduction, or simply surviving a difficult season with limited food nearby. One successful giant squid kill flips that entire equation. Instead of dozens of separate hunts, each carrying its own risk of failure or wasted effort, a swordfish gets one enormous nutritional reward from a single committed attack. Even accounting for the real danger involved, a fish capable of pulling this off gains a massive head start on its overall energy needs for weeks at a time, assuming it survives the encounter with only minor injuries. This trade-off likely explains why evidence of these encounters keeps surfacing specifically among adult swordfish, rather than smaller, younger individuals. A young, inexperienced fish probably lacks both the size and the raw speed necessary to survive a serious mistake against an opponent this large and this well-armed. A fully grown adult carrying more muscle mass and years of hunting experience stands a much better chance of landing a clean strike and walking away with an enormous reward rather than a fatal injury. Every high-risk strategy eventually produces losers as well as winners though, and this particular gamble is no exception. For every mark left behind by a squid that escaped, or a swordfish that struck cleanly and swam away successful, other evidence tells a very different story, one written directly into the broken remains of a weapon that failed at the worst possible moment. Sometimes the clearest proof of a violent encounter is not a scar at all. It is a broken weapon left buried inside the very animal it struck. Marine researchers studying stranded sharks have documented this exact scenario more than once. In several recorded cases, a blue shark washed ashore, carrying the snapped-off tip of a swordfish's bill lodged deep inside its own body, sometimes embedded near the skull, sometimes buried in the torso, evidence of an attack violent enough to shatter solid bone on impact. In at least one especially striking case, researchers found the broken tip driven directly into the shark's nostril, having punched cleanly through cartilage before finally snapping under the force of the strike. Careful examination of these wounds revealed something researchers had not fully expected either. In some cases, the shark had clearly survived the initial attack by a meaningful stretch of time, with surrounding tissue showing real signs of healing around the embedded fragment rather than fresh recent trauma. That detail means at least some of these encounters end with both animals surviving the immediate impact, only for one to carry a broken piece of the other around permanently. A strange, silent souvenir of a fight neither side clearly won outright. These documented cases involve sharks rather than giant squid specifically, since sharks wash ashore and get examined far more often than a soft-bodied squid ever does after a similar encounter. Still, the underlying lesson applies just as clearly to any target a swordfish attacks with full commitment. Even a weapon this strong, capable of punching through solid ship planks centuries ago, can still fail catastrophically under the right conditions, snapping off entirely and leaving the swordfish suddenly without its primary tool for both hunting and defense. Losing part of the bill mid-strike creates an immediate serious problem. A swordfish relies on that weapon for nearly every successful hunt afterward, and a shortened or damaged bill likely reduces both reach and striking power significantly. Beyond the practical hunting impact, an open wound at the point of breakage also creates a vulnerable opening on an otherwise armoured, streamlined animal, a weak point other predators might exploit if the injured swordfish crosses paths with something dangerous before fully healing. Scientists studying swordfish bone structure discovered something surprising while investigating exactly this kind of damage. The bill is not simply solid, static bone sitting passively at the front of the fish's face. It contains living tissue capable of slow, ongoing repair, similar in some ways to how a mammal's bone quietly rebuilds itself after a minor fracture over the following weeks and months. That discovery raises an important question worth exploring on its own. If a swordfish can genuinely survive losing part of its most important weapon during a fight, this dangerous, what actually happens to the fish afterward? And how does an animal built entirely around speed and precision continue hunting successfully while missing the single tool it depends on most? A swordfish missing part of its own bill should, by every obvious measure, struggle to survive very long afterward. Researchers studying the biology of this bone expected something fairly rigid and unchanging once they examined it closely, similar to how many people picture bone in general, hard and largely static once fully grown. Instead, they found something closer to living, active tissue, constantly being broken down and rebuilt in small amounts through a natural process called bone remodeling. This same basic process helps human bones slowly heal after a minor fracture, laying down new material gradually over the following weeks to restore some of the original strength. What made this discovery especially surprising involved how the repair markings actually looked under close examination. In most mammal bone, remodeling leaves behind fairly large, easily visible structures as evidence of the repair process at work. In a swordfish bill, researchers found these same repair structures present, but shrunk down to roughly 1/10 the usual size, packed far more densely throughout the tissue. Despite being smaller, testing showed the bone remained remarkably stiff and difficult to break, comparable in raw strength to bone found in a horse, an animal many times the swordfish's own size. In a swordfish, this remodeling process appears capable of repairing minor damage along the bill over time, gradually reinforcing weakened areas and potentially helping the structure recover some strength after smaller cracks or chips. A complete catastrophic break near the tip, the kind documented in stranded sharks carrying an embedded fragment, likely represents permanent damage that this slow repair process cannot fully reverse. Smaller amounts of wear and stress, the kind a hunting swordfish probably experiences regularly throughout a long life spent slashing through prey at high speed, seem to fall within a range this remodeling system can genuinely manage. This finding helps explain something researchers had wondered about for years. Given how often swordfish drive this weapon into solid, resistant targets throughout their lives, the bill should logically accumulate serious structural damage over time, eventually becoming too weak or too short to function properly. Instead, adult swordfish generally maintain a strong, functional bill throughout their entire lives, suggesting this quiet, ongoing repair process works constantly in the background, largely unnoticed, keeping the weapon sharp and structurally sound despite years of repeated violent impacts. A swordfish that survives a truly catastrophic strike, losing a significant portion of its bill entirely, likely faces a much harder road ahead regardless of any repairability. Hunting success probably drops substantially with reduced reach and striking power, and the fish may need to shift towards smaller, easier prey simply to survive while whatever tissue remains slowly adapts to its new, shortened shape. Understanding how this animal survives physical damage from a fight only tells part of the story though. Surviving the fight itself means surviving the crushing environment surrounding it, a world where pressure alone poses a threat serious enough to destroy human engineering built specifically to withstand it. At 2,000 feet down, the ocean pushes against every square inch of anything caught there with roughly 900 pounds of force. To put that number in perspective, most modern military submarines are built to operate safely only within this same general depth range, somewhere around 1,000 to 2,000 feet, using thick steel or titanium hulls specifically engineered to resist exactly this kind of relentless crushing pressure. Push a submarine meaningfully beyond its designed limit, and the hull can fail catastrophically in an instant, collapsing inward under a force powerful enough to destroy advanced human engineering within a fraction of a second. Engineers designing these vessels spend years calculating exactly how thick a hull needs to be at any given target depth, then build in significant additional safety margin beyond that calculation, just in case of small manufacturing flaws or unexpected stress. Even with all of that careful planning, submarines still remain limited to depth that a giant squid or a hunting swordfish treats as an entirely normal, unremarkable part of an average day. A swordfish and a giant squid experience this same crushing pressure constantly, with no metal hull, no reinforced structure, and no engineering team calculating exact safety margins in advance. They survive it anyway, and the explanation comes down to a basic difference between their bodies and a submarine's design. A submarine needs air-filled space inside to keep its human crew alive, creating a serious pressure difference between the crushing water outside and the comparatively low-pressure air trapped inside. That difference is precisely what generates the destructive force capable of causing an implosion in the first place. A swordfish and a giant squid carry no equivalent air pocket working against them. Their bodies stay filled almost entirely with water and soft tissue, allowing internal pressure to rise and fall in step with the surrounding ocean rather than fighting against it. Without that dangerous pressure imbalance, there is nothing left inside their bodies capable of collapsing inward, the way a submarine's hull eventually does. This single structural difference explains how two animals without a submarine's steel armour can casually swim through water, dense enough to destroy some of the most advanced vehicles ever engineered. It also reframes the entire fight these last several chapters have described. These are two animals fully adapted to an environment that would instantly kill or crush almost anything else, engaging in a violent struggle inside conditions humans can only reach using multi-million-dollar equipment built by entire teams of engineers. That environment alone should make this rivalry feel remarkable. What makes it genuinely strange is just how consistently the evidence for it keeps turning up in the exact same form on opposite sides of an entire planet. Two fishing communities separated by an entire ocean and thousands of miles of open water kept independently documenting the exact same mystery for years before anyone connected the dots. Workers at a small market on Cape Cod noticed circular scars appearing on certain swordfish coming through their doors, mostly during the colder winter months, and slowly built up their own informal understanding of what the pattern likely meant. Thousands of miles away in the Pacific, an entirely separate group of fishermen and researchers noticed remarkably similar markings on their own catches, working with completely different squid populations native to their specific stretch of ocean. Neither group set out looking for this pattern deliberately. Both discovered it simply by paying close attention to animals they already handled constantly as part of their regular work, noticing something unusual repeating often enough that it eventually demanded a real explanation rather than a shrug and a quick dismissal. That kind of grassroots accidental discovery carries real scientific weight, precisely because nobody involved had any reason or motivation to manufacture a pattern that was not genuinely there. Word travelled slowly at first, passed along through casual conversation rather than any formal research channel. A market worker mentioning the marks to a curious customer. A fisherman posting a photograph online simply because the scarring looked unusual and he wanted someone else to explain it. These small, informal exchanges eventually reached people with the training and background to recognise exactly what they were looking at, turning scattered anecdotes into something researchers could finally take seriously and investigate properly. Once researchers eventually connected these separate observations, the wider significance became much harder to dismiss as mere coincidence. Consistent scarring, showing up independently among fishing communities working oceans apart, with no direct contact or shared assumptions influencing what they were looking for, points towards something structural about how swordfish and large squid interact wherever their two ranges happen to overlap, rather than one bizarre, isolated local event confined to a single, unusual patch of water. This global consistency also opened the door for a new kind of research entirely, one built less around formal scientific expeditions and more around everyday people already working closely with these animals. Citizen scientists, fish market workers, and commercial fishing crews, most with no formal marine biology training at all, became an unexpected but genuinely valuable source of evidence simply by staying observant and sharing what they noticed with researchers willing to listen carefully. This kind of collaboration between working fishermen and university scientists remains fairly rare in most fields of marine biology, yet it produced some of the clearest and most consistent evidence found anywhere in this entire investigation. That kind of widespread, crowdsourced evidence naturally raises a bigger and more difficult question. If this pattern really does show up wherever swordfish and giant squid overlap, exactly how often is this violent encounter actually happening out there in the dark, hidden from view every single night? Ask two different marine biologists how often this fight actually happens, and you may genuinely get two very different answers. One side of the debate points toward relative rarity. Only a small fraction of examined swordfish carry these particular scars, meaning most individual fish likely never encounter a giant squid large enough to leave a lasting mark at all throughout their entire lives. From this perspective, every documented case represents a genuinely unusual event, a rare, high-risk gamble a swordfish takes only occasionally, likely driven by unusual hunger, unusual opportunity, or simply being in the wrong stretch of dark water at exactly the wrong moment. Researchers on this side of the argument point toward how carefully fish need to be examined before a scar even gets noticed in the first place. Most commercial processing moves quickly, focused on preparing fish for market rather than searching skin carefully for faint circular marks. If scars only get documented when someone happens to look closely enough, the true number of marked fish passing through these same markets every season could easily be higher than anyone has formally counted so far. The opposing view treats that same scarcity very differently. Scars only prove an animal survived the encounter, telling researchers nothing at all about how many similar fights ended with the swordfish losing outright and never making it back to any fisherman's boat for examination. Under this reasoning, visible scars represent only the encounters with a specific kind of outcome, a wounded survivor, while an unknown and potentially much larger number of total encounters simply vanish from the record entirely, their evidence sinking to the ocean floor along with whichever animal failed to survive. Settling this debate with real confidence would require something researchers currently do not have: reliable direct observation of these animals interacting regularly over an extended period of time across a wide stretch of deep ocean. Until reliable, long-term deep-sea monitoring technology becomes cheap and widespread enough to deploy at that kind of scale, scientists remain stuck estimating frequency indirectly, using nothing more than scars on survivors and the very rare filmed glimpse of either animal moving alone through the darkness. For now, most researchers studying this specific question tend to land somewhere between the two extremes, treating the encounter as neither a vanishingly rare freak accident nor a routine nightly occurrence, but something happening with real, meaningful regularity in specific overlapping hunting grounds, particularly wherever seasonal squid populations and swordfish migration patterns happen to intersect closely. Whatever the true frequency actually turns out to be, one thing remains completely certain, regardless of which side of this debate eventually proves correct. The evidence gathered so far proves this rivalry is real, physical, and repeatedly happening in real time somewhere in the deep ocean, even while the exact numbers behind it stay stubbornly out of reach. Step back from every individual scar, every broken bill, and every rare video clip explored throughout this story, and a clear line begins to separate what scientists can genuinely confirm from what still remains a complete mystery. Confirmed facts anchor the entire investigation. Sharks and swordfish both carry scars matching the sucker patterns of large squid species. Sperm whales hunt giant squid regularly, leaving thousands of undigested beaks behind as undeniable physical proof. Both a swordfish's bill and a giant squid's beak represent genuinely dangerous weapons, each fully capable of seriously injuring or killing the other animal in a direct encounter. Both species share the exact same extreme deep ocean environment, hunting through identical crushing pressure and identical total darkness, night after night. Layer these confirmed facts together, and a coherent, evidence-backed picture genuinely does emerge, even without a single piece of direct video footage showing an actual swordfish versus squid encounter. Scientists rarely need to witness an event firsthand to build real confidence in a conclusion, provided enough independent physical evidence points consistently in the same overall direction. Every scar, every broken bill fragment, every documented feeding relationship adds one more supporting brick to a structure that, taken as a whole, stands up remarkably well under scrutiny. Beyond that solid foundation, the story shifts quickly into far more uncertain territory. Nobody has ever filmed a swordfish and a giant squid actually fighting, meaning every single detail about how the attack unfolds, how long it lasts, or how frequently either animal wins outright remains built from careful inference rather than direct observation. The true frequency of these encounters stays genuinely unknown, caught permanently between the two competing scientific interpretations explored earlier. Even some of the largest, most dramatic scars found on record cannot always be traced back to one single confirmed species with complete certainty, given the very real possibility that a closely related, even less studied squid might be responsible for at least some of them. This mixture of solid fact and genuine mystery is not a failure of scientific research. Deep ocean biology, especially involving animals this rare and this difficult to observe directly, almost always works this way, building a careful picture from indirect clues long before any direct observation ever becomes possible or practical to obtain. Understanding a hidden underwater rivalry through scars and broken weapons is, in many ways, remarkably similar to how paleontologists reconstruct extinct animals almost entirely from fossilized bone fragments, filling reasonable gaps with careful inference while remaining honest and upfront about exactly where solid evidence actually ends. What makes this particular mystery genuinely compelling is not a lack of real evidence at all. It is the sheer scale of what remains completely unexplored, an entire hidden world of violent, high-stakes encounters playing out constantly in one of the largest, least understood environments left anywhere on the entire planet. Two animals fighting somewhere in total darkness might seem like a small, isolated story, interesting mostly as pure spectacle rather than something carrying any larger meaning. Look closer, and this particular rivalry actually says something important about the health of the entire ocean. Both the swordfish and the giant squid sit near the top of their local food chains, meaning their population numbers and general health reflect much broader conditions playing out across the wider deep ocean ecosystem surrounding them. A thriving population of large, healthy swordfish generally signals a healthy, functioning food web extending far below them, one with enough prey, enough oxygen, and enough overall balance to support large, energy-hungry predators successfully. The same basic logic applies just as strongly to giant squid populations living in these same general waters. Changes in either population can act almost like an early warning signal for problems scientists might otherwise struggle to detect directly, given how difficult and expensive it remains to monitor deep ocean conditions across such an enormous, largely inaccessible area. A sudden drop in scarring evidence across multiple fishing regions, for example, might eventually signal a meaningful shift in squid populations, prey availability, or even water temperature patterns long before more obvious warning signs become visible anywhere closer to the surface. Studying interactions between major predators like these gives scientists a genuinely useful window into how energy and nutrients actually move through this deep, largely hidden part of the ocean. Every giant squid successfully caught and eaten by a swordfish represents a meaningful transfer of energy, moving from smaller prey species up through the squid itself and finally into one of the ocean's fastest, most far-ranging apex predators. Multiply that single transaction across an entire ocean and an entire year, and these individual violent encounters start adding up into something with genuine ecological significance, well beyond simply being two isolated hunters colliding once in the dark. There is a human stake buried in this story too, one worth taking seriously. Swordfish represent a genuinely significant global commercial fishery, supporting fishing communities and food supply chains across multiple countries and continents. Understanding exactly what these fish eat and how much energy and effort that hunting actually costs them helps scientists and fisheries managers make better, more informed decisions about how to manage this species sustainably for the long term, protecting both the animals themselves and the people who depend on them for their livelihood. Beyond the science and beyond the economics, this rivalry also captures something people have always found genuinely compelling about the natural world. Two powerful, evolved predators, each perfectly adapted for its own specific environment, meeting in total darkness where almost nothing about the outcome is ever guaranteed in advance. That basic story, uncertainty and raw power colliding somewhere just out of sight, has drawn human attention and curiosity for as long as people have looked out at the ocean and wondered exactly what might be hiding underneath the surface. Somewhere beneath the surface right now, past the point where sunlight gives up completely, this same ancient struggle is almost certainly playing out again. A swordfish patrols through freezing water it should not be able to hunt in effectively at all, kept sharp and alert by a strange biological trick evolved millions of years ago, specifically for this exact purpose. Somewhere nearby, a creature people once dismissed entirely as myth drifts silently through the same total darkness, watching for exactly the kind of danger this particular fish represents, using eyes larger than anything else alive on the planet to buy itself every possible extra second. Everything explored across this entire story, the speed, the warm eyes, the bladed weapon, the basketball-sized vision, the crushing pressure neither animal even notices anymore, exists specifically because these two predators have been colliding somewhere in the deep ocean for an extraordinarily long time. Neither evolved in complete isolation. Each shaped the other across countless generations, building weapons and defenses in careful response to exactly the kind of threat the other one represents. Most people will spend their entire lives standing on a beach or a boat deck, staring out at calm, ordinary-looking water, with absolutely no idea what this same ocean actually contains just a few thousand feet straight down. The scars on a shark photographed off Hawaii, the strange rings pressed into a swordfish pulled from Cape Cod waters in the dead of winter, the broken bill tip found lodged inside a stranded shark on a completely different coastline. Each of these small, individual pieces of evidence represents a fragment of a much larger, mostly invisible war playing out constantly. Just beneath waters, people swim in, fish in, and sail across every single day without a second thought. Consider everything gathered across this entire journey, starting with a single fast-moving shape, crossing open water at highway speed, and ending here with two of the ocean's strangest predators still locked in a struggle nobody has ever fully witnessed from start to finish. That distance, from a simple fish with a pointed nose to an entire hidden ecosystem shaped by fear, weapons, and survival, shows exactly how much depth can hide behind something as ordinary looking as calm, blue water stretching out toward the horizon. This particular rivalry remains far from fully understood, and it may honestly stay that way for a very long time. But the next time you look out across open ocean, remember exactly what sits beneath that deceptively calm, unremarkable surface. Somewhere down there, right now, speed is colliding with size, bone is colliding with beak, and two of the strangest, most powerful predators the ocean has ever produced are once again finding each other in the dark, continuing a struggle that started millions of years before either species ever crossed paths with a single human being.